right, line S1, we're taking a look at learning task number 3, where we are going to go and describe our HVAC energy management systems. And there's not a ton to cover inside of here because, to be honest, most of the time we're not going to be the ones involved in setting this up. On a small scale, if it's going to be a residence or something like that, we might do as much as programming a thermostat, just because our customer maybe doesn't understand how to do it or has requested that as part of the job. But for the most part, most of what we're going to see over here is just a description, which is what the ITA requires, that you understand what our different types of energy management are going to be. So we got 3 main types that we're going to go over. The first one over here is going to be our time-based management. And time-based management basically says, hey, when is your building active? When it's not active, shut off the unnecessary lights. This is no different than, your dad coming into your room and saying, shut off that light if you're not using it. It's like this thing where why would we have lights and unnecessary equipment on if we're not using it at any time? There's massive amounts of time that, offices, buildings, etc. are going to be unoccupied, just weekends and out of office hours themselves as well. Do this through the use of time clocks usually. If we have got overall building management systems, we do have some that will manage all the lights and everything like that. It all gets tied together. Individual users still have a light switch inside of their office, but we've also got ways that we can go and shut off, the entire thing just remotely or through a computerized system. In those cases, the building manager, whoever's in charge of that, should be the one that's going to be setting off, these things that they're going to turn off automatically. If they do get turned off and you happen to be working late, you can always turn those lights itself back on. It does still provide for individual controls. The next type of management that is presented is something that's called duty cycle savings. Duty cycle savings are where we are going to just cycle loads on and off. Now, these are going to be things that are going to happen during our usage hours. So they could be applied with time of day. We could have time of day scheduling where we're going to turn stuff off outside of office hours. We can also go and have duty cycle savings. They're not independent of each other. They are independent of each other, but they can also be combined into the same overall, saving scheme. This is just where you're going to cycle certain components on and off so that you don't run them continuously. Examples of these are going to be heat or other things that they carry through, but we don't necessarily need to have them on all the time. Some ventilation fans and stuff like that. If you're still getting your proper cubic feet per minute that you're pulling out of a building, you're going to go and shut some of them down, then you're going to turn them on and move them again, shut some down, turn on and move the air again, etc. So it's just going to be an on-off where we are shedding some of our load through that. The other one that we have over here is going to be called optimal start savings. And this relies upon, whatever I have for my HVAC system to be monitoring what my outside temperature is going to be. If my outside temperature is far out from what my indoor is supposed to be, so indoor we're usually looking for 21 degrees, but if let's say it's outside is about 5 degrees, I'm going to have to start that early to go and ramp up and build my heat inside of the building in order to go and, make everything comfortable. If, however, it's summertime and, by fairly early in the morning, we're already sitting at about, 18 degrees, I can delay that start. I can just run along at low loads, and then all of a sudden, right before it starts up, I start up because it's only going to take me a little bit of time to go and make up for that amount of heat that we are going to have. This is just going to be optimal start savings. It's the same as optimal stops that we're also going to be able to do the same thing. Once again, if my indoor temperature was 21, my outdoor was 18, I could shut that down early before office hour ends because then it's going to still ride through, we're not leading a lot of heat through our building envelope or anything like that. All 3 of these, the optimal start savings, the duty cycle savings, as well as the time of day schedule savings, can all be combined into the same overall energy management scheme. It is going to take somebody who knows what they're doing to go and set that up, and you don't want to be shutting on and off non-critical loads. You have to be thinking about things like illumination safety as well. You can't just shut off all of your public lights, washrooms, those things usually don't have windows, so you don't want to be shutting those off as part of it. Or there should be night lighting inside of them, things like that. So it needs to be done intelligently, but there are ways that you can use your HVAC systems or your building control systems to go and cut down on the amount of usage, because ultimately the amount of usage that we are going to have out of our HVAC system is going to be reliant upon what we have inside of the building. Lights produce heat. If it's summer, I don't want to have unnecessary lighting on because that's going to be producing heat. So all of it ties together under the same system. They do go after that into a little brief thing about programmable thermostats. Everybody has seen a programmable thermostat at this point. If you are a homeowner that works outside, not that that happens anymore these days under COVID, but if you had an office job that you would go off to, what you could do is you could program your house that it's going to drop the temperature inside while you're away, and then you're going to have it automatically heat the house up again by the time that you come back home, etc. Yeah. I'm not going to go over the top of the settings inside there. Just the standard for those is going to be 21 degrees that we are going to have as our indoor standard. That's what you've all become accustomed to, over the years inside of schools and inside of your houses and things like that, is that 21 degrees. And so us, as North American humans, feel accustomed to that. Different societies have different, indoor air temperatures that they set them to. Different parts of the world will just set these things to different ones based upon what is deemed as comfortable, and people just kind of adapt. So if you are going to set anything up for customer, 21 degrees, target temperature. All right, let's talk about computer-based systems. Computerization of our HVAC is going to be what we will mostly see. We don't have a lot of old school analog controls. Pretty much everything is going to be run through a networked type of system. We have the ability to monitor absolutely everything. We have the ability to run specialized programs. You can have different programs that are going to change based upon dates, daylight saving times, all of those other things that you don't have to manually override anymore. And altogether, what we will have is we'll have a system that is oftentimes referred to as our DDC system, which is going to be a direct digital control. Direct digital control is similar to what you may have heard before referred to as a PLC. PLC is a programmable logic controller, and it's basically an open source type of component. It's not actually open source, but what it is, it's just a bunch of inputs and outputs, and you choose what exactly it is that you want any of those inputs and outputs to do. And you create your own screens and, GUIs, the graphical user interface, all that other stuff. You do that inside of a PLC. What a DDC system is it is a pre-programmed PLC that instead of you having to go and assign pins and all that other stuff inside of there, it just has, check boxes. This pin's already assigned to it. You're going to go and attach to specific terminals on each of my DDC controllers. Those individual DDC controllers, all we do in the software is we state, what this is connected to that, etc. So it's a mostly pre-programmed. We just tell the DDC system then that this input is going to be a temperature sensor, and it is in this room. And then the DDC, categorizes it and makes everything control off of that. Usually, these are going to be what we refer to as a network type of system. Over here, we see a couple of DDC components over here. This first one over here is my return air DDC controller, so it's going to handle all of my return air. Everything that is coming out, the stale air from inside. Then I'm going to go and have another DDC over here that is going to be my supply air. It's going to handle all the fresh air that we are going to take in, all of the mixed air that we are going to take in, and then it is going to go and supply that back into the building itself. And the last DDC section that I have over here is going to be my heating and cooling that I'm going to have. Now, we know that the supply air, from what we've covered before, supply air does need to be able to control the heating and the cooling, but these are completely different components that we have from here to here. So what we have is all of this is going to go and get assigned onto a network. Over here we've got a router, and then this LAN stands for local area network that we are going to have. Really, there should be a separate line from this router to each one of these. We don't T-tap off the lines. That's always going to run you into problems. What we can then do is we can monitor all that from something else that is going to be connected onto there, whether that's going to be an actual PC or whether we do it remotely. They show a laptop over here. You can go and dial into these systems. Well, not dial in. We don't dial into anything anymore, but you can log into these systems. Just VPNs, things like that are all going to be very common through the control systems. Because we've got them laid out like this, we're now going to be able to go and see each of my individual components as well. And I can, from one of these remote stations, I can take a look. What's my outside air temperature going to be looking at? What is it looking like right after my heating coil? What is it looking at like right after my cooling coil, etc. I can monitor every single one of those individual ones. I do see that my room thermostats are going to be connected up to my supply air controller. Now, in a lot of cases, we are going to go and have multiple rooms, and these rooms are going to be done off of what we refer to as an addressable or a looped type of system. If I've got a single DVC controller for the entire building, I will run what is referred to as the loop, and it's going to be a serial communications loop that is going to go from thermostat to thermostat to thermostat, and inside of each of these, I'm going to set an address, 1, 2, 3, and then inside of my software, I would go and type in room number 1 is going to be, our thermostat number 1 is in this room, and that room also has got this heating and cooling manifolds over here that are going to be controlling the air that go into it. Because in a lot of cases, these are spread throughout the building, all of these manifolds. It allows us to do a lot of network control. Let's take a look at some of our components over here because they are labeled out with some cool little components. First of all, let's start with this one up top over here. This is a variable frequency drive. The variable frequency drive will go and take an AC motor, and by changing the frequency output onto that motor, it can change the speed of that motor. We know that the fan speed controls the amount of airspeed that we are going to go and have, and it's also going to be that cube, that relationship that's going to be to the horsepower that's going to be required. So what we want to do is if we don't need to have a lot of airspeed, we want to go and drop our airspeed because we're really taking away from the total amount of watts that our system itself is going to be using at that point. We do that all through a variable frequency drive. That variable frequency drive has got a number of components over here. And these ones down here are names that you should be familiar with as an electrician. AI, AO, DI, DO stands for digital input, digital output. That's going to be my DI, DO. And then AIAO is going to be analog input or analog output. Anything that is going to be a continuously variable scale or a sensor, or if I'm running, that I've got to have a speed signal that goes from 0 all the way up to full speed. All of that is going to be analogs that I'm going to go and use. Digital are going to be, they're sometimes referred to as discrete as well. They're highs or lows. It's open or closed. It's a switch has been triggered or a switch has not been triggered. We're going to run all of those into my VFD over here. Now, where they have got these lines over here, the DIDO, they're actually referring to this, the terminals that those conductors are connected to on here. And it is only one line. They're not showing, the line of the return. Each of these has to be a complete circuit still. But what they're talking about over here, let's start with the top one. We'll just analyze the first VFD. The top VFD over there, the DI is going to be, I can't actually do that. I thought I could do something here in my software, but I can't. Digital input that I'm going to go and have for that one is going to be a digital input into this board. In other words, it's going to be a feedback. And what it's going to be is it's going to be a feedback of any sort of an alarm state that happens inside of my VFD. So I'm going to go and have an alarm relay inside there that's going to be either open or closed. If the VFD would have a fault, it's going to close that relay usually, and that's going to go and send in an alarm. So that's going to be my digital input into this DVC controller. My digital output that flows out from here is going to be a switch that is basically going to turn on the VFD. Anytime that we want to run this thing, I'm going to send out a discrete output, a digital output that will be a closed switch, and inside of the VFD's got its own little microprocessor inside there. It's going to read that and say, hey, I'm getting a signal to start. Let's do this. Next one down there is going to be an AI that I'm going to have. This is going to be an analog input back into here, and it's going to be a speed feedback. In other words, it's going to go and tell my HVAC controller how fast this fan is actually turning. We're going to try and tell the fan to turn at certain speeds, but if there's a lot of back pressure, let's say that I've got failures of my dampers that are closing or something like that, what could happen is that I develop a lot of back pressure, and therefore my fan is not going to be able to run as fast. So I'm going to go and run that back into here and say, whoa, my fan is not performing nearly as high as it should. I should check other stuff or set up an alarm or something like that. I'm also going to, on another one of my analog inputs into the DDC, monitor my motor amps that I'm going to go and have. Once again, just for protection sake, that if for whatever reason I start to overload it, that I can shut that thing down and protect that motor. Last one that we have is going to be my speed control, and that's going to be an output. That's going to come out of my DDC. So it's going to be an analog output going into that VFD, and it's going to be some sort of continuously variable. It's either going to be a 4 to 20 milliamp signal. You'll learn about those inside of fourth year, exactly how they work, or usually 0 to 10 volts. It's going to be one of those two, 4 to 20 being our more common one that we have. That covers the interfacing of our VFD, which is the motor controller, back into our DDC. This one over here is going to go and have the same setup for my supply fan VFD, and then my supply air DDC controller is also going to go and have a bunch of other analog inputs that they're labeled on here, and you can go through each of those individual ones that we will have over here. A couple of the ones that I do want to point out, these are going to be inputs coming back in. So this is an analog input going in. They show the arrow over there. My damper over here is going to go and have an analog output, and it's going to have an analog input. The output is going to run the actual damper motor itself. The input is going to be an end switch that where I'm going to be monitoring to go and see how far. It's not going to be a physical end switch in a lot of cases. These are going to go and be electrical signals that are going to tell me how far open or close I'm going to go and be. I do also have a couple of other components. This one over here, I want to go and take a look at, number 13. This is referred to as a differential pressure sensor. And if you take a look at it closely on your diagram, it's hard to see on here because it's so small. What you see on that is it has got little arms poking up like that, and then it's just going to be labeled as being my differential pressure sensor. What it is it's actually got a tube, a sensor on this side. It's going to have a tube, a sensor on this side, and it is going to go and measure the difference in pressure. Literally, these two tubes are going to be connected through into a small diaphragm in the center, and whichever side has got the higher pressure is going to go and push the diaphragm over. It's going to be a small bendy diaphragm. We attach that to an analog sensor so that we can go and read what it's going to be. The reason that we use a lot of these differential pressure sensing is differential pressure sensing is going to tell us this filter states. We will use them, we will see these things on filters, we will sometimes see them on coils as well. Because if I build up a lot of crud on that filter coming into there, all of that crud is going to go and change the amount of air that goes through. So I'm going to, over here, where my supply fan is trying to push air through, it's going to create a vacuum. It will drop my pressure on this side, and it is going to be higher on this one. And so I'm just going to go and set a range, and I'm going to say that, hey, when my pressure difference across there is more than this, I'm going to call for, maintenance, so for a screen change or a screen clean or check or whatever it's going to be. Same with my coils, the actual hot water and cold water coils themselves. We will oftentimes see them over top of that. It's an easy way for us to electrically, without having to go into like optical recognition or anything crazy like that, for us to electrically monitor the state of any sort of filtering. Okay, all of this ties together. It is going to be a lockdown system. We are not going to go and have control over it for the most part as electricians ourselves. These are usually going to be managed by, large companies, Honeywells and things like that, that will go and send their own technicians out who will do the final hookups. In most cases, for us, what we will have is we are going to go and have control locations, and we are going to be in charge of running conduits to them sometimes, as well as power that we are going to need to run. Obviously, we would need to run power to the VFD over here. Some of these, like damper motors, we are going to need to run power to them as well. The analog signal will control that. And then we're going to go and just build those conduit paths. In most cases, they're going to get pulled in by the actual HVAC technicians. They'll take care of all the termination. Or in some cases, they just run all those cables through that plenum ceiling. If you look at the components that are inside of here, it looks more complicated on the surface when you see, all the different wires and components over here. But really what we are seeing is the exact same physical components: exhaust, mixed, outside air, supply fan, coil, return air. All of the same things as what we saw inside of our previous system, just with more monitoring, capabilities, differential pressure sensor, flow, all these sort of things like that we can do to, increase the reliability of our system. The guts of the system still work the same way. Heated water or chilled water, that is going to be run through there. That chilled water can be chilled through a refrigerant cycle, where we actually just have a heat exchanger with a refrigerator coil that's buried inside a tank, so we can chill down that water. The same with the water can be heated through boilers, etc., but it still just runs through one of these systems over here. This is going to be the most common types of HVAC systems that we will have for an overall building will be done through something like this. A lot of our rooftop units, we talked about those at the very beginning of commercial HVAC, a lot of our rooftop units are going to go and have communication software that is going to be built into it. Not the low end ones, cheap small ones for small commercial places, but a lot of our larger ones will have that. And so they've got all of this that's already going to be built inside of it. And usually then it's just going to be a single Ethernet network connection out. So we'll bring power up to that thing. We will bring an Ethernet cable up to that thing as well. And we'll bring that Ethernet cable down to wherever the router is going to be from those rooftop units. It allows them to do, once again, just monitor all components inside there. All right, last section inside of here talks about metering, alarms, and load shedding. Heating and cooling of a building is a massive cost. Talk to you, if you don't pay your own hydro bill, talk to whoever does pay the hydro bill and ask them about, the differences between summer and winter with AC and heat on, and they will go into usually a long rant about the amount of energy taken. So what we will do is we need to monitor and watch that, because in a lot of cases, you're going to go and have a demand limit. BC Hydro will sell you as much power as you need, provided it doesn't go and screw over their system. But in a lot of cases, what they have going into your facility is they've got a single transformer that's feeding a bunch of others. And what they have to do is they have to balance all that. So they'll say, hey, we're giving you a peak of this, we're going to give you a peak of this, we're going to give you a peak of this. And as long as all three of you don't exceed your peak demands off of that transformer, we're good to go. But if all three of you would, we would have burnt out transformers and power outages and stuff like that. So they'll set a demand limit, and if you exceed that demand limit, then they're going to go and penalize you, charge you extra money. So what we will do is we will take non-essential loads and we can go and categorize them through our building management into deferred loads, stuff that can go and happen later on. And the way this happens is we monitor it through, we're going to have CTs that are going to go, current transformers, that are going to go onto my main lines back at my main system coming in. So if I got a three-phase system, we're going to have our 3 lines coming in. We're going to have a CT around each one of those. This is then going to be a digital monitor that's going to go and say, see what's going on there, and it's going to have control over top of some other types of components. And it will go and turn those components off until we're below whatever our deferred load is going to be. Now, there's 2 different ways demand limit is set. One is where BC Hydro says we're going to bill you. The other one is based off of your actual size that you are going to have. Where we will see these now is going to be in this thing called a load miser. It's a term for something that was made by a company that was actually called Load Miser. But what it was a way that we could hook up multiple components so that we don't overload a system. Where we see these used now is in the advent of electric vehicles. Because electric vehicles take a lot of power to go and charge up, particularly if you got a fast charger, so you can't be running everything. You've got a lot of people that have like a house that might be sitting on close to 70, 80 years old. It's got a 100 amp panel inside of there. Maybe it's a heritage home, so they can't even go and do a massive renovation to it, but they want to buy an electric vehicle. And in order to go and charge that, they need to go and have a 30 amp charger. And we just cannot add that onto that existing 100 amp panel that's already probably maxed out. So what we will do is we will go and take their dryer, we'll cut into that circuit, and we are going to go and place in a load miser, which is going to be doing what we're talking about over here. The load miser is simply going to be a 3-way switch that is going to go and monitor. So this load miser is going to have either in itself, or some of them, the fancier ones, energy management systems they are referred to in the code book, are going to go and have something that is going to go and monitor around here. And then they're going to say, hey, we want to charge your vehicle, but we can't charge your vehicle at the expense of everything else inside of the house. So if you're not using your dryer, we can go and run the charger. Or if you don't have over top of 100 amps. And so it'll shut off non-essential loads. Your car should be able to charge overnight as long as everything else is, kind of shut down for the evening. So, yeah, we see the same thing where we have set a demand limit based upon, in this case, my system ampacity. And instead of allowing my demand based upon all the heat and everything else to go over top of that, I will go and defer some of my other load during times of peak heating. If it's during the day, I'm going to go and defer the charger. And then at night, when you can turn all your baseboard heaters off because you can use blankets, then you can go and charge them up. All right, that's that for Learning Task 3.